Welcome to this episode, where we're diving into the fascinating world of micro-machined levitated gyroscopes and the fundamental noise that limits their performance.
Yeah, it's a pretty deep topic, but really important if you're curious about how tiny sensors measure rotation with incredible precision. So let's start with the basics. Gyroscopes.
Right, so gyroscopes are devices that measure rotation or angular velocity. You find them in everything from airplanes to your smartphone, helping with navigation and orientation.
And micro-machined levitated gyroscopes, or MLGs, are like the high-tech, miniaturized versions. They have a spinning rotor that's suspended without any physical contact, using electromagnetic levitation.
Exactly. That contactless suspension is a big deal because it means less friction, which should mean better precision. But, as the paper points out, even these advanced gyroscopes face fundamental limits due to something called mechanical thermal noise.
Mechanical thermal noise. That's basically the tiny random fluctuations caused by thermal energy, right? Like molecules bumping into the rotor and causing it to jiggle ever so slightly.
Yeah. Imagine trying to balance a spinning top on a table that's shaking just a little bit. That shaking is like the thermal noise. It causes tiny random torques on the rotor, making it wobble and limiting how precisely the gyroscope can measure rotation.
So no matter how perfect the design, this noise sets a floor on performance. You can't get below it because it's rooted in fundamental physics.
That's right. Now, one of the key concepts the paper discusses is angular position stiffness. It's basically how strongly the rotor is held in place by the suspension system.
And this stiffness can be positive or negative. Positive stiffness is like a spring pulling the rotor back to its center position. It stabilizes the rotor.
Whereas negative stiffness is more like a spring pushing the rotor away from the center, which can actually make the system less stable and increase noise.
The paper highlights that this stiffness comes from the electromagnetic levitation system, which can be inductive, electrostatic, diamagnetic, or hybrid.
And the type and value of this stiffness dramatically affect the noise behavior. Positive stiffness tends to keep noise limited, but negative stiffness can increase noise by orders of magnitude.
That's a big deal because it means the design of the suspension system directly impacts how precise the gyroscope can be.
Another important factor is friction, which is a major source of energy loss and noise in mechanical systems.
In MLGs, friction is controlled by the vacuum level inside the gyroscope package. Better vacuum means fewer gas molecules bumping into the rotor, which means less friction and less noise.
But here's the catch. The paper shows that even with a perfect vacuum, noise can't be reduced indefinitely. There's an intrinsic property called the gyroscopic coupling coefficient, related to the rotor's inertia and rotation speed, that sets a lower limit.
So vacuum helps, but only up to a point. You can't just pump out all the air and expect noise to vanish.
Exactly. Now, the paper uses a metric called angular random walk, or ARW, to quantify noise. ARW measures how much the gyroscope's output randomly drifts over time due to noise.
Lower ARW means better precision. The paper derives formulas showing how ARW depends on rotor speed, moments of inertia, stiffness, and damping.
And the key insight is that increasing rotor speed and rotor inertia reduces ARW, improving performance.
But if the stiffness is negative, ARW can increase dramatically, which severely limits performance.
That's why electrostatic gyroscopes, which often have negative position stiffness, tend to have higher ARW and correspond to tactical grade performance.
Whereas inductive gyroscopes usually have lower stiffness and better ARW, reaching navigation grade performance.
The paper also discusses Johnson noise and the Ising criterion as two ways to understand the gyroscope's resolution. Basically, the smallest rotation rate it can reliably detect.
Johnson noise is originally an electrical noise concept, but here it's applied to mechanical torque fluctuations caused by thermal energy.
The paper uses Johnson noise theory to calculate a fundamental limit on resolution, showing it depends on damping and stiffness.
The Ising criterion, on the other hand, is a qualitative method stating that the energy involved in measurement must exceed a certain thermal energy threshold for reliable detection.
Both methods agree that angular position stiffness is the main factor limiting resolution.
But the Johnson noise approach depends on damping, while the Ising criterion doesn't, so they provide complementary perspectives.
Together, they define a confidence tolerance range for the gyroscope's resolution.
It's interesting how these two different approaches converge on the same key parameter, stiffness.
Yeah, it really highlights how crucial controlling stiffness is for improving gyroscope performance.
The paper also compares these theoretical predictions with actual MLG prototypes reported in the literature.
Right. Electrostatic gyroscopes tend to have negative position stiffness and higher ARW, so they're generally tactical grade.
Inductive gyroscopes have lower stiffness and better ARW, reaching navigation grade.
The paper even explains observed phenomena like motor-induced noise at certain rotor speeds as related to dynamic compensation of stiffness.
Despite all these advances, measured noise is still higher than the ideal theoretical limit, which means there's room for design optimization.
Another important concept is the scale factor, how much the gyroscope's output signal changes per unit of rotation rate.
A higher scale factor means it's easier to detect small rotations.
The paper compares scale factors of levitated gyroscopes with vibratory gyroscopes, which are another common type.
Vibratory gyroscopes currently have higher scale factors and have achieved tactical grade performance.
Levitated gyroscopes have lower scale factors, but can potentially improve by controlling position stiffness and rotor angular momentum.
But to reach tactical or navigation grade performance, levitated gyroscopes need extremely low position stiffness, which is a challenging engineering goal.
The paper suggests hybrid contactless suspensions combining inductive and electrostatic methods to better control position stiffness.
Another idea is using spherical rotors, which naturally have zero position stiffness, potentially reducing noise.
Although spherical rotors maximize gyroscopic coupling, so noise is still limited by rotor design and speed.
So precise control of position stiffness is really the key to pushing MLG performance further.
And while vacuum and rotor speed help, fundamental physical limits tied to stiffness and gyroscopic coupling remain.
To wrap up, understanding mechanical thermal noise and its relationship with stiffness and damping is crucial for advancing micro-machined, levitated gyroscopes.
These devices have the potential to revolutionize navigation and sensing with ultra-high precision.
The research provides a roadmap for improving design and understanding fundamental limits.
Hopefully, listeners come away appreciating the delicate balance of forces and noise in these tiny, high-tech devices, and how physics sets boundaries on what's possible.
Yeah, it's a fascinating glimpse into the challenges and opportunities in precision sensing technology.
Thanks for joining us for this deep dive.
Until next time.